Hi, everybody. I'm Puttagunta. I'm the technical program manager at Linaro. And today I'd like to discuss about the secure playback using OptE. It's more of an overview. So what is a problem statement, right? So we want to be able to open a browser, log in to a website like Netflix or Amazon, and play the secure DRM videos. And nobody even in the middle or even after hacking the device and booting the device should be able to access the decrypted or the decoded content. Like, that's our holy grail, right? And obviously we want to do this all with the best performance possible without any mem copies or any buffer copies. So that's the problem statement. And the objectives for this session are to basically give an overview of what are the main components that are involved in the secure playback, and how do they interact with each other at a high level, right? So I'm not going to go into depth of each of these big components. Fortunately, we have another 5 presentations in this Connect that deal with each of the individual components. And I'm going to bring up the references as we go along. So before going to the secure playback, I want to understand what is the technology that makes this possible at kind of a hardware level. So you have the ARM Trust Zone technology, and you have the Trust Zone address space controller kind of IP that can protect blocks of memory in the DDR. And you have a Trust Zone protection controller. It's another IP that can protect certain peripherals, secure peripherals on the SoC. So again, so this level of topic about the introduction of the ARM Trust Zone, how the basic OptE works. There's a presentation by Victor Chung later on today, and he talks about how the secure world works, secure boot works, and how basic trusted application works. So I'm not going to go into the depth of that, but essentially, what is ARM Trust Zone, right? It's a feature of the ARM CPU, right? And just like a CPU has a user mode and a privileged mode, it also has a secure mode. So it's actually a mode in the CPU. And if you have like a client application that wants to do something in the secure world, like decrypt the buffer or something like that, and wants to pass something, then it triggers an interrupt. It's a secure monitor interrupt, and the CPU context changes and goes into the secure mode. And then what is a Trust Zone address space controller? Address space controller, this is more of an IP block. The Trust Zone address space controller is an IP block from ARM, but it doesn't necessarily have to be. Different SoC companies have their own IP blocks. But essentially what it is, it's an IP block that sits in between the CPU and the DDR, right? So, and you can program the Trust Zone address space controller IP only when the ARM CPU is in the secure mode, right? So you can say, okay, this 100 megabytes chunk in the DDR, this 100 megabytes chunk in the DDR, and this 10 megabytes chunk in the DDR are protected. So from that point on, the Trust Zone address space controller won't let those accesses go through unless it's coming from us when the CPU is on the secure side, or another host is on the secure side. So it's not necessary that it's only protecting the access from the CPU. It's also can be protecting access from, like, for example, a DSP that's doing the video acceleration. And then you have a similar IP, a Trust Zone protection controller. Again, this is another IP block from the Trust Zone protection controller is ARM terminology, but it's an ARM IP, but it doesn't have, it could be SoC specific. They could use their own IP, but essentially what it does is it blocks off access to peripherals, like a real-time clock or a timer that needs to be secured. And again, it is only programmable from the secure side when the CPU is in the secure mode. I just wanted to show this picture. Victor's presentation is going to go a little bit deeper into this. But this is how essentially the communication with the trusted application on the secure side works. You have the application in the user space, and you have the Linux kernel, and all of them are in the normal world. And then you have the secure side, and OptE core operating system is running on the secure side, and the corresponding trusted application is also on the secure side. And if I'm an application, right, and I just want to be able to do some decrypt on the secure side. So what I do is, I set up the trusted application that does the decrypting part or whatever on the trusted application side. And from the client, I make calls from the Opti client, and it goes to the Opti Linux driver in the kernel. That triggers the SMC call. The CPU changes mode, and then the Opti OS is the one that it knows that this call is associated with this particular trusted application and routes it. So at a high level, that's how it works. All right, so now that we got the key technologies that enable this, you have the trust zone, which is a CPU feature, and then you have a trust zone address space controller, and that's an IP block that protects memory, and you have a trust zone peripheral controller. So, what should happen? In plain English, what should happen when you want to play a secure media? The first thing you want to do is negotiate the license, right? And the license has the key to decrypt the data. You got to decrypt the data. So that's kind of the first phase. And then, like any other playback, you need to decode the data. You probably need to scale the data or color convert the data. And you want to render the data. So now going back to the first phase, like what is a DRM system, right? A digital rights management protection system. It's a solution that provides the capability to license securely distribute protected content, right? So whether it's Google Widevine DRM or Microsoft Player AD DRM, there are mechanisms in place that make sure that the content being delivered is secure. And it could be decrypted, it could be played. And CDM is another term that keeps coming up, which is a content decryption module. And that is the module, think of it like a wrapper around a DRM solution. Like you have a Microsoft Player AD DRM or a Widevine DRM. CDM is a wrapper around it so that applications above the CDM, it looks more consistent, whether it is a Widevine DRM or a Microsoft Player AD DRM. And then the other key term that needs to be understood is W3EME. What is it, right? It's basically an HTML5 extension, and it provides an API that enables the web apps to interact with the DRM provider and CDM. So, more simple terms, what it is, you have an HTML5 and JavaScript application, and this API specifies how to talk to the CDM, the content decryption module, through the browser. So they're basically standard API call. It standardizes the API to talk to the CDM via the browser. And obviously, the browser needs to implement the EME extensions, like a Chromium browser implements the EME extensions. Or are we doing that? Any idea? So obviously, the browser that you're using needs to implement the EME extensions. And the EME API, it does not enforce which DRM should be used, right? It's almost like a plumbing that it just provides the pipes between the CDM and the licensed server. So if you go to like w3.org and look at what EME is, you have a browser, right? And this is the application, which is typically like the HTML5 and JavaScript application. And that's the device boundary, and then you have the web server and the license server on the top. You have the content delivery network on the other side. And then this is an independent application like a content decryption module, right? So this is the wrapper around the Widevine DRM or the Player AD DRM. And it's important to know that what the EME spec specifies is the JavaScript application API to the browser, right? So these are like if you look at the update message, create session, these are the APIs that EME specifies, right? So the application could basically register for a callback. So if a browser actually sees an encrypted stream, if the application JavaScript application registered for the callbacks, it will make that callback, and then it will make the connection to the content decryption module. So now, how a content decryption module talks to the browser or vice versa, that is not part of the EME spec. So that's important. right? Because different browsers have different ways to talk to native applications. So this is not part of the EME spec. That is, right? So again, like, if you look at it from the JavaScript application side, right? And you use this API, it basically provides a pipeline, from the content content decryption module to the license server, right? So in reality, the JavaScript application doesn't really know what the messages that are going back and forth between the content decryption module and the license server are. It just knows that, okay, this is the way I talk to the content decryption module, set up the link to the license server, and it's completely up to the content decryption module and the license server how to talk to each other. Like Microsoft Playback DRM might have certain messages going back and forth. The EME specification itself doesn't care, right? So, I mean, why do they do that? They want to make sure that the system works regardless of what DRM solution is being used. And the other thing to note also is that from the JavaScript application perspective, it only thinks that it's talking to the content decryption module, right? It sets up the pipes, and it only thinks that it's talking to the content decryption module. It really doesn't have an idea of how the video is getting played, right? It thinks that the CDM is doing all the magic, right? So it doesn't care whether the media pipeline in the browser is playing the video, or a GStreamer plugin is playing the video. It doesn't care from the JavaScript application perspective. So how does it fit into the vision that we're after, right? So, here you have a browser, and you have the EME extensions implementation in the browser, and you have the content decryption module, and you have the web application on the top, and this is the device boundary, right? And you have the license server on the top. So basically, whatever I just said before, it sets up the pipeline to the content decryption module. And again, it depends on the DRM in place. It's up to the wideband DRM or the Microsoft Playback DRM to say, okay, it has to query the device capabilities and know what what kind of decryption it can handle and that kind of enumeration. And for that kind of, for the CDM, it needs to be able to talk to a trusted application on the trusted side, right? So once the license is set up, then the license server says, okay, I provided the license. Now I'm going to start streaming the data. So the streaming data actually is coming from the CDN, which is the content delivery network. So, and at that particular point of time, the encrypted frames are coming in, right? And they're just getting routed to the content decryption module. And the content decryption module is the one that's decrypting the data, right? And it obviously has to talk to the secure side to be able to decrypt the data. Well, it doesn't have to, but you can use OpenSSL kind of decryption or, a symmetric decryption on the user space. But what we are after is, then if you do it on the user space, then the decrypted buffers are exposed to the user space, right? But if you don't want that to happen, then you obviously have to go to the trust zone. And then what you get back, the dotted line that I'm showing up, is you're sending the frames that are encrypted. What you get back are not the decrypted data, but you get references to the buffers that are decrypted, right? So that's important. And the DMA buff, I'll talk in a little bit, but that's important. It's important to note that what we're after is to make sure that the user space or even the kernel cannot access that data, right? So now, all right, we talked to the license server, we got the license, we're starting to get encrypted frames, and we are starting to decrypt them. What's the next thing, right? So a couple of keywords are V4L2 based hardware accelerated decoder. What's V4L2? Video for Linux version 2, and it provides an interface of the kernel boundary for the video codecs, right? And if you it's the API at the user space. What is beautiful about V4L2 is it makes the user space API very, very simple to the kernel, right? I bought the Chromebook from ARM, and Samsung was one of the companies that pioneered in it, obviously. And I could just, when I brought up the kernel, you just see /dev/video11 or something like that as a decode node, right? And then I could just open the file, and I could just query what kind of capabilities that particular decoder had, and set up the buffers, and you can start queuing the buffers, and you can start unqueuing the buffers, right? So there are a lot of confusions about like what the decoder does, where is the state management, where is the state of the playback managed. The important thing to know is that V4L2 based decoder, the only thing it cares about is decoding the content, right? You're giving it encoded data in buffers, and then you're just getting the decoded content back. It does not want to do any state management. Like if you press pause button, it doesn't handle any of that. Like if you want to do lip syncing with the audio, it doesn't do any of that, right? It's simple decoder. That's all it does. And the expectation is that the user space framework, like a GStreamer or a StageFright or a browser, does the synchronization part, right? And V4L2 supports, different kinds of buffer, whether they're memory map buffers or DMA buffer file descriptors. It already supports it right now. So, typically a V4L2 client driver is the one that's talking to the DSP side, right? Like, or a video accelerator, right? And the key thing is the DMA buff file descriptors, right? V4L2 already supports DMA file descriptors, and in general, that's the direction that things seem to be going, of exchanging buffers across applications and across the kernel boundaries are these DMA file descriptors. And again, DMA file descriptor is more of a reference to a buffer, right? It's not a pointer to a memmap buffer. And the good ELC presentation, or there's a presentation on V4 Linux by one of the Samsung guys. Very good presentation. Highly recommend it. And then what is GStreamer, right? Now GStreamer is a pipeline-based media framework, right? It's a framework where various decoders and encoders can be plugged into, right? You basically, you could implement a VP9 codec and plug that into the GStreamer. And if you implement a V4L2 based decoder, you can write a plugin for that and put it into the GStreamer. You put it as a GStreamer plugin into the GStreamer. And the great thing is, as of GStreamer 1.0 release, V4L2, if your SoC implements V4L2 driver, you don't almost have to touch anything in the user space. I didn't have to touch anything in the user space. GStreamer just worked. Why? Because GStreamer, they standardize the interfaces across the talking to the V4L2 node. So the open calls, ioctl calls, querying about what capabilities the decode has, it's all standardized. So, and the good thing, even better thing, is that the V4L2 plugin is already part of the GStreamer project now. Right? So that's the best thing about it. Now Chromium. Chromium is the open source web browser project from Google. And Google Chrome, as we know, derives the source code from that. And what is a Pepper? Another term that's important is the Pepper API, Pepper plugin API. And it was started in Google as a way to address portability and performance issues with the NPA API. And it's basically an API to talk to the native applications, right? If you have a GStreamer or some native application or a CDM or anything, right? The way that a browser can use that capability is using the Pepper plugin API, right? So we talked about the V4L2 based hardware accelerated decoder. We talked about the GStreamer, which is the framework, and we talked about Chromium. So how does this fit into the work that we're doing here, right? So you have the browser, you have the GStreamer, and the GStreamer is plugged into the media stack, into the Chromium browser using the Pepper plugin API, right? And then you have the video for Linux 2 based decoders in the kernel. You have a V4L2 based color converters in the kernel. Example is libVP, VPE engine from TI, or any other color conversion or a scaler that can scale the images. And then you have a graphics engine. And so the GStreamer pretty much becomes part of the browser itself, and then at that particular point of time, the DMA buffs are transferred back, and the decode happens. So you're basically queuing up the DMA buffers to the V4L2 decoder. You're queuing them back. Okay, now you have the decoded data. You probably need to color convert it. You probably need to resize it. You send back the DMA buffer file descriptors onto the V4L2 color converter node. You get the scaled images, and then you render them. You send it to the renderer. Right. So all the data exchange is being happening through the DMA buffer file descriptors. And the key thing is the user space cannot see the actual data. Right. So, one thing to note is that the GStreamer is currently, LHG is working on plugging in the GStreamer into the Chromium browser. So there's a talk on that from Zoltan and Christophe Berzou tomorrow. And did I tell you about the content decryption module the presentation on that? That there's a presentation on the content decryption module and the EME and how that, I think we'll be doing the clear key implementation is given by Matt Snowby. That's tomorrow too. And this GStreamer plugging into the media, into the Chromium browser is being given by Zoltan. And there's another key thing, right? The key thing is the DMA buffer file. Today, in open source, there's not, the DMA buffer file descriptors doesn't have the infrastructure in place to tell it that it's secure. Like, how do you handle it, right? So that's an area that LMG is starting to look at, right? So you have a DMA file descriptor. And the other thing that is not in any of these pictures is like where do you get the buffers from, right? So you could use an allocator, right? For first thing, you probably want, you probably have to use something like a trust zone address space controller to block, to block off certain area of the memory and allocate buffers from that pool, right? But the thing is, you don't want to reinvent a memory allocator in the secure side, right? So, for example, CMEM, there's a presentation given by Gil Pitney day before yesterday on CMEM, and it takes care of the pool, the pool allocation and the memory allocation inside that pool, and that exposes a DMA file descriptor, right?
Currently, it doesn't expose the DMA buffer.
But you're working towards that goal, right? So that's the first part, and now the second challenge is going to be how to secure that buffer, or, that entire pool, right? So, so the one presentation that there's a Benjamin Gannard, one of the ST assignees in Linaro. He was supposed to give a presentation on that. How do you tell a DMA file descriptor that it's secure, and once the DMA buffer is received by the V4L2 decoder, how do you tell? How do you ask permission for that DMA file descriptor? Because you want access to that buffer, at least on the DSP side, right? Because that's where the decoding actually gets done. So that, he has certain proposals for that. And unfortunately, he's not able to make it to Connect. We'll try to see if he can record the presentation later and put it online. Any questions so far? Yes?
Yeah.
Probably.
Okay, I have a couple of questions. Number one, that slide that you show on that DDR separation,
Yeah.
right, where the trust zone address controller, actually we have to give the area specific to the DDR that this is a protected area, right?
Yeah.
Where the secure data will come. Now, do you have to do it at the boot time, or dynamically I can change the address limit of the secure DDR?
You have an answer for that, Gil?
I'm sorry.
His question was, how do you carve out that? Is it a carve out at boot time, or can it be allocated in runtime?
One comment I was going to make first was that CMEM is possibly one of the methods to allocate buffers. And on Android, you have ION, and there's DRM, and there's a Tyler kind of allocator. So, TI has a CMEM, but there's other ways to allocate the memory.
Yeah, so you could use ION or whatever mechanisms you use.
But
right.
if you're using CMEM, then yeah, we use CMA, and you can reserve some CMA blocks at boot time with a little stub that we have.
But you could do it in the driver too, right?
From code, or you can do a carve out.
Yeah.
And give it a mem equals
Right.
Size at address and carve out some memory from Linux.
Okay.
And then we manage it from there.
Okay.
But that's one. CMEM is just one.
One of it. I mean, like, you know,
for
CMM is a
allocating.
solution. Ion allocators does the same thing, right?
No,
It's
the,
similar.
the reason I asked is I was just thinking that suppose initially I blocked around about 120 meg of data, 120 MB of data address I blocked, right? Where I know this is my secure area and nobody else will access. But later maybe I'm not doing anything with respect to security. Maybe I'm running some games and etc. So in that case, can I release that memory and use it for games which will again will not be not secured now? It will be used right now.
I mean, I'm not necessarily an expert on it, but I know at least one implementation of secure playback was runtime changing whether some memory area was protected or not through secure monitor calls into trust zone. So only in the trust zone environment can you change that, but you can change it at
But
runtime.
it's runtime changeable, right? If you look at the trust zone address space controller, it is programmable at runtime, right?
And I guess it also depends on the IP block you are using because it can be customized.
Yeah. So the number of, like, for example, the number of sections that you can block off is dependent on trust zone address space controller, you know, the implementation of it or another IP, right? But that's an independent problem, right? You know, there's a whole discussion about how, you know, obviously nobody likes carving out the memory, right? But ideally, we all want to get to a point where I can reserve some memory at runtime. That's a different problem, right? But once you decide how do you secure them is more of what I was, and how do you allocate buffers from that particular pool is more in this discussion.
Excuse me. I've got a related question. So, but what is the standard in the sense? Is there a recommendation that I mean? So typically, like when we typically reserve during boot time, you know, as part of like your kernel startup route or something, we would assign so much of address for the static buffers that we allocate. But what is the general rule in a sense when working with something like this? Like, do people try to leverage like dynamically changing the secure buffers out in and out depending on what's going on, or is it typically like you just allocate your boot and that's then call it a day and use that throughout the?
I don't know about the secure use case so much, but I mean that's why CMA was developed so that the kernel can migrate pages when your buffers aren't being used.
Okay.
So, but beyond that, I don't know. I don't know the.
I mean, from a
ramifications of
security side, so that's
changing
one part of the problem. You know,
changing the security.
obviously we're talking about a chunk of memory, right? Let's just say that beginning of the use case you want to do that because you kind of know the parameters of your use case. But once that is done, we have to make sure that a certain chunk of memory is secured, right? Not every single, you know, the granularity within which you can secure things is not like, it's not like you have like a 4 kilobyte buffer and on dynamically fly you just want to secure that. That's not, that's what I thought would happen, but actually when I looked at the specs for the trust zone address space controller, the number of blocks it can secure is actually limited. So you probably want to secure like, you know, 100 megabytes of memory or something like that, and then you want to allocate from that pool, right, that is already secure from the kernel, Linux kernel side, right?
Thank you for that. That was very clear. You keep using the word secure, but you're using it in a very odd way. You don't really, normally security is protecting my computer against stuff on the internet that I didn't want to run. And what you actually mean is Trojaned throughout this entire presentation. This is we're going to a lot of trouble to make sure the code running on my machine is what you want and not what I want.
Yeah.
But it's just a very peculiar use of the word secure.
Yeah, I mean, that's another.
Yeah, not about how it technically works.
What I mean secure is, like, you know, in the problem definition, that's why
you mean trusted by the license provider rather than trusted by the computer user.
Right.
I mean, I guess if it's your computer, then If you only lent me the box, then fair enough. But if it's my computer, then I'm not very impressed, obviously.
Yeah, I know. Yeah, so I mean, like, this presentation, I wanted to just focus on the problem statement of, like, what are the objectives, right, from their perspective, to protect the content, right? Now, whether the content should be DRM protected or not, that's not part of this conversation, right? All right, so, okay, so we talked about how the decode happens, and the buffers are exchanged, and then, again, this is how it all comes together, right? Again, you have from the top, you have the W3CEME standard, HTML5 extension standard, that talks about how the web application can, the API from the web application to talk to the content decryption module through the browser. That's what that specifies. You use that to set up the pipe between the content decryption module and the license server. You get the license, then you start getting the data from the content delivery network, and then you start decrypting the data. And then the content decryption module gives back the decrypted data, buffer handles up, and the GStreamer is plugged into the buffer into the browser framework using the Pepper plugin API, and the thing that all puts together in the end is the DMA buffer being able to secure the DMA buffer using the DMA buffer file handle. So, like I said in the beginning, this presentation is about providing an overall view of what components are there and which component talks to what component. And this is really the map, right? And the good thing is we have other sessions that go on that deep dive into each of these topics, right? For example, how does when I talk about a trusted application, what does that really mean? How do you know that a particular application is trusted? How do you sign it? How does a secure boot work? That all is covered. And how does a simple client application talk to that particular corresponding trusted application? That is part of V's presentation later on today. And then there's the implementation of the EME standard and the wrapping around of the content decryption module around a certain DRM. Right now we're using the clear key DRM, and that is being presented by Matt Snowby tomorrow. And then plugging in the GStreamer into the Chromium browser using the Pepper plugin API is being covered by Zoltan and Christoph tomorrow. And how do you make the DMA buffer descriptors itself secure? I forgot to update the name, sorry. But that was actually planned, was planned to be given by Benjamin Gannard. He's not here, unfortunately. But that's really a very key component of this use case. And obviously, the one that you don't see in this picture is that memory pool. Like you have a memory pool of about 100 megabytes or whatever that use case you may be. Once you block that out, allocating from that secure space is part of one of the challenges that we're going to have to take on. And that's so Gil Pitney's presentation happened on Monday, 3 p.m. So do take a look at that. He compares a little bit about the CMEM comparisons with ION. What are the advantages of different allocators? What are the challenges? So that was a good presentation. It's recorded, so you can probably look it up. So that's the presentation that I had. Any other questions?
I have a quick question. Is there any performance? Oh, thank you. Is there like a performance? Or what is the performance impact of having to do all of this? Additional like trust zone type work. Is it? Has anyone done any analysis of that?
So, one thing I got to remind is, like, this is not stuff that's already in the lab right now. This is what we're shooting for, right? For example, the use case of a simple client application tucked into the trusted application, that is already implemented, right? We have a reference implementation for that. Matt Snowby's presentation about the content decryption module and integrating that into the EME, that's work in progress right now by Matt Snowby. The GStreamer plugin GStreamer getting plugged into the Chromium browser, that's the work that Zoltan is doing in LHE. Now, the work on the V4L2 buffer passing, I got to talk to you later. There's work that's already been done, but it's just not upstream. That's the work that Linaro, we're trying to propose to upstream and get it upstream.
Okay. And in the context of like 4K data, has there been any work done by anyone so far, like trying to use trust zone to process 4K data? No? Okay.
I would guess really the overhead
I guess the overhead is really just decrypting the encrypted bit stream, right? I mean, on top of that, you got a bunch of like secure monitor calls and stuff, and that's roughly equivalent-ish to a system call in terms of overhead. I mean, kind of hand wavy, but I mean that doesn't scale with respect to video size. That scales with respect to number of calls you make and stuff, and that's going on at a rate of at most 30 FPS. So I shouldn't expect an issue.
Any other questions? Okay. Thank you.